We are going to balance these reverse faulted blocks. This is a footwall block which is rigid, and here is a movable and deformable hanging wall block. Here the transition from flat to ramp and the transition from ramp to flat is smooth curve shown here and over there. As a response of this smoothness, when the hanging wall block was pushed, it climbed up and has produced a round hinge fold. This fold geometry, there is no guarantee that it is an arc of a circle. So, we treat it as an irregular curve. We are going to balance this cross section. Consider this line as a loose line final orientation. Since a compression has brought this loose line here, the loose line initial must be to the right hand side. Now, we have to find out the area of this irregular geometry. A simplification was made in drawing. This segment of flat is taken parallel to horizontal line, this segment of flat is taken parallel to the horizontal line, and this segment of the flat and this portion of the hanging wall block has been considered to lie on the same line. We have seen how to find out the area of irregular geometry, and that we are going to apply on this place. 2 points are marked, point small a and point small b, and the AB length is equal to 5.7 centimeter. Now, the AB line will be divided into equidistant short segments of lines and marked by points. I am taking 0.5 centimeter of interval. We will drop normals. How many lines we have drawn? And a tiny line here, 11. There are 11 lines. We want to find out the sum of their lengths. This is 13.1 centimeter. Therefore, the area within this region is given by 13.1 divided by, we took 11 lines, so divide by 12 multiplied by the AB length 6.2 centimeter square. We have to measure the CD length, which is equal to 3.5 centimeter. Now, we divide the area 6.2 centimeter square by 3.5 and it turns out to be 1.8 centimeter. Extend this line to 1.8 centimeter. I mean to say that this length is 1.8 centimeter, and from here drop a normal on this plane. Now, the cross section has been balanced. We can say that this is a loose line initial, and after deformation this is the geometry of the deformable and movable hanging wall block, but before deformation its geometry was like this, and by saying that the restoration is complete. What has happened? The area loss over here due to compression, movement of loose line initial to the loose line final position has led to area gain here. We have assumed no area has been lost and no area has been gained overall. Therefore, the area loss here is equal to the area gain there. What about this area? This area is a common area in the initial and the final condition. Therefore, we did not bring into the calculation. Note that this length CD multiplied by, say this point is R, CD multiplied by dr is the area of the rectangle, and that is equal to the area calculated here. Take an example of a fault propagation fold. In this case, this portion is a flat, this is the ramp, the fault movement direction is shown. This is the foot wall block, this is the hanging wall block, and here is the fold produced at the surface. The fault tip is over here, which has not reached the surface. Therefore, this fault R, the ramp portion, can be called as a blind fault. Now, how to balance the section? In this case, one might note that the surface geometry is like a box fold, whereas at depth, suppose we have information that it is a kink. Here nothing to worry about this portion, we can focus only on the box fold portion, and as I demonstrated, we can find out the area over here, and then taking the loose line somewhere here, loose line final, we can locate the loose line initial to be running from this point, loose line initial, and then drop a normal. Do it in a manner that this area of the rectangle is equal to that of the trapezoid, and finally say that before deformation the block looked like this, and in this way one can take care of fault propagation fold. The situation in case of a fault bend fold is that we do have a trapezoid here, and inside towards the core of the fold the trapezoid geometry persists. You can look at the fault bend folds ideal sketches that I have already shown you. There the fold geometry does not change from the exterior towards the core of the fold. There also the same principle will work. So, there is no new drastic way of solving in case of fault bend and fault propagation folds. Let us balance this normal faulted block. Here is a normal fault which is curved, therefore, we call it Lystric. Before faulting, this block must have been joined with this block. This is the foot wall block and this is the hanging wall block. If this block was attached here, this line, we can call it loose line final, must have been somewhere here, and that during deformation the loose line has shifted. Remember, normal faults are products of extensional tectonics. We need to find out the area bound within this irregular geometry. A simplification has been made in this diagram. This flat is taken horizontal, therefore, these two lines are parallel. This portion of the flat is parallel to this, and the ramp to flat transition here is smooth, whereas I have drawn it here, which is a sharp contact between the ramp to flat. To find out the area, I join these 2 points, say this is point A, that is point B. Now, AB line is to be broken into smaller segments with 0.5 centimeter interval. Then I will drop normals on these points on the AB line. We have considered total 7 lines, this is a tiny line. Here a question comes, should I count this dashed line as number 8 line? And to avoid this question, one could have drawn or chosen the AB line in a different way. For example, if this was the starting point, one could have chosen AB like that. This is point A and that is point B. In that case, we can divide the AB line into lines of equal segments of 0.5 centimeter length and draw normals on those points. Here, this is the loose line final, and we have considered how many lines 1, 2, 3, 4, 5 and 6. What is the sum of their lengths? And this is equal to 13.9 centimeter. Here the AB length is equal to 3.2 centimeter. Therefore, the area is 13.9 multiplied by 3.2 divided by, we considered 6 lines here, so divide by 7, it is 6.4 centimeter square. Now, we want to find out this length. Small AB length is equal to 3 centimeter. Now, if I divide this area by the AB length, 6.4 divided by 3 is equal to 2.1 centimeter. In case of reverse faults, we were finding the loose line initial in this direction, away from the fault. This is the fault. So, away from the fault we were finding the loose line initial, whereas in case of a normal fault such as this, we have to find out the loose line initial position towards this direction. The reason is obvious. The loose line initial was here. By faulting due to tectonic extension, it will shift away from the fault in case of normal fault. Therefore, this length 2.1 centimeter I have to draw in this direction. This AT distance is equal to 2.1 centimeter. From T I will drop a normal, and now say that what was finally a normal faulted block such as this, before deformation the block was like that, a perfect fit is made, and in this process the normal faulted block has been balanced. So, what has happened here? This is the area gain when this kind of movement took place. This is a schematic presentation that the block has moved, internal deformation of the block also happened. This is the area opened up, result of that the loose line initial moved to the loose line final position. Note that the AT distance multiplied by AB distance is equal to this particular area calculated. In this way, the area balance is maintained.